Okay, so we're going to be doing standard 2.2, which is on expectation values of measurements. And we're going to be doing problem 2.7 out of McIntyre. The problem starts off by saying a spin-1 particle is in the state psi, which can be represented as the scaled column vector, 1 over root 30 times 1, 2, 5i. And part A states what are the possible results of a measurement of the spin component as z, and with what probabilities would they occur, and to calculate the expectation value of this spin component operator. And we know by experimentation that the possible measurements are 0 and then plus or minus h bar, and we know that these are the eigenvalues of the SC operator by postulate 3. We can calculate the probabilities of these measurements by using this result that we've been using all semester. And since we're working in the SC basis, we can represent the 3 eigenstates by the row, so column vectors, the row vectors here because we have the corresponding bra, but the kets can be represented as 1, 0, 0 for positive h bar, 0, 1, 0 for 0 h bar, and 0, 0, 1 for negative h bar, and that's what these 3 bras here are representing. So we can calculate the probability of measuring positive h bar as followed, and the calculation is the modulus squared of the row vector 1, 0, 0 times the scaled column vector 1 over root 30 times the 1, 2, and 5i. And when we do the calculation through, we get 1 over 30. And now when we're taking the probability of getting 0 h bar, we do a similar calculation and get 4 over 30. And the probability of measuring negative h bar is 25 over 30. These probabilities add to 1 as we expect. Now to calculate the expectation value, which is the average, we can do this following calculation by first operating has z on the ket psi, and then taking this new ket and taking the inner product with the bra of psi. And this is represented as h bar over 30. The reason we have this h bar over 30 in the front is we get an h bar from the SC operator, and we get a root 30 from both the row and column vectors here, which gives us this constant out front. And then we have this row vector 1, 2, negative 5i, which is the adjoint of this column vector. And then we have the operator, which is represented as 1, 0, 0, 0, 0, 0, 0, 0, negative 1, and then 1, 2, 5i once again. First we operate this matrix on this column vector, and we get the new column vector 1, 0, negative 5i. And then when we take the inner product here, we get negative 4/5 h bar. And this makes sense because if we go back and look at our state vector, we have a large probability of measuring in the negative direction, therefore we do expect something closer to negative h bar. So now we're going to do a similar calculation as we just did, but we're going to do it by calculating the expectation value of the spin component Sx. So we're going to look at the x component operator this time. So we're going to use an identical approach by operating in the similar ways we did before, but now we have an h bar over 30 times root 2. This is because of the h bar over 2 that comes from the S sub x operator in matrix representation form. So now we do a similar calculation. We have the adjoint here of this column vector. We first operate and get the column vector 2, 1 plus 5i 2, and then we take this inner product and we get the expectation value for the spin component Sx of 2 over 15 root 2 times h bar. And that'll be it. So thank you.